My presentation will be on the Dantzig-Wolfe decomposition and the Bender's decomposition. We will begin by explaining Dantzig-Wolfe in rather extensive detail, and then explaining Bender's more broadly, as we will discover they share many similarities. Before we dig deeper into the Dantzig-Wolfe decompositions, we need to emphasize some ideas. The first idea is delayed column generation. This is a technique that is used in this decomposition and allows us to save a significant amount of computational time. When running the simplex method with a given basis, we can improve our computational efficiency by only generating the column when it is in the basis, so we no longer have to store all the columns in memory. You will see this implemented with. The second idea is simply an observation of convex properties. Suppose we have a convex region as shown on the screen. We see that every point on this convex set can be represented as a linear combination of the extreme points and extreme rays. Rays, a ray in the region is any ray that can be drawn such that it will always be bounded by the region. And an extreme ray is any ray whose points cannot be a linear combination of the other rays. These extreme rays are always on the face of some boundary of the convex region, as they are here. So we can take a look at the point 2, 3. 2, 3 can be represented by the extreme points 2, 0, and 0, 2. The multipliers on these two extreme points are both 0.5, and we note that they both sum up to 1. The extreme ray is 1, 2 with a multiplier of 1. Now, suppose we have a new constraint that makes this feasible region smaller. We note that any new constraint added cannot increase the feasible region. It can only reduce it. So there are no new points in this new convex region, and that weren't already in the old region. So any point in this new region can be represented as a linear combination of the old region's extreme points and extreme rays. So now let's dig deeper into the actual Dantzig-Wolfe decomposition. The problem must be in the form such that there exists blocks on the constraints where no two blocks share the same xi values. There also exists a master problem that contains xi values from all the blocks. There are several slightly confusing notational details that we should go over. And this is how we'll be writing our notation for the rest of the presentation. The xi's are vectors in R and I, where ni is the number of variables in the ith block. AJI is a matrix that has a width of ni and a length of mj. Notice that if we ignore the master problem, we have k independent problems, one for each block. And that's simply because none of the blocks have any common x variable values, so they are completely separate from each other. The general idea is to find solutions from individual blocks and bring them back to the original problem. However, we cannot immediately do this because although there is a way to know if a solution from a block will be feasible when we bring it back to the original problem, we don't know how the feasible region of each block will change with the master constraints added. So the corner points, we can't iterate through the corner points. Well, we can't iterate through all the corner points with the simplex method. So we have to change the problem in such a way so that we can run the simplex method directly on the blocks, and we'll know immediately if the vertices that we get from that block can enter the basis for the original problem. This is an independent problem for block J. The constraints will give us a feasible region Qj. Now remember from earlier, every point in the feasible region can be represented by the extreme points and extreme rays of that region. Vjh is the hth extreme point in Qj, and dji is the ith extreme point in Qj. We let lambda j be a vector of length uppercase nj. Unfortunately, I forgot to write nj on top of the first summation, but it should be there. And uppercase nj is the number of extreme points in the feasible region. Similarly, mu will be a vector of length uppercase rj, where rj is the number of extreme rays. And rj should be the top of the second summation, and capital Nj should be at the top of the third summation. We see that the feasible region Qj is defined by the extreme points and extreme rays. Since this is the only block that has any variables from xj in the original problem, the solution for the original problem will be from the region Qj if we just look at the part of that final solution that contains variables from the block xj. Of course, we are not forgetting the fact that there are constraints in the master problem that may change the feasible region. However, we noticed earlier that those constraints can only reduce the region of Qj. That means we can still represent the part of the final solution that contains variables from the jth block by extreme points and rays of Qj. We can go even further and replace all the xj values with extreme points and rays. So any constants multiplying the values in xj in the original problem are now going to be multiplying the xj representation with extreme points and rays. Thus, we can rewrite the problem like so. Notice the same ideas apply to the constants in the constraints multiplying the xj parts from each block. Summing the lambda jh over h must equal 1 for every j to satisfy the properties for each region Qj. So we add that at the bottom as well. Visually, we can redepict this as follows. Now it looks like we've complicated the original problem. There are far more variables now. The variables are now the lambdas and the mu's. So running the simplex method could work, but it would be even more work than the original, and it would take up a lot of space with all these new variables. But this is where we utilize column generation. Instead of storing all the columns, we only create columns that are in the basis and assume the rest of the column variables are 0, so we don't need to deal with them. We now need to start off with a basic solution. We can simply run the following LP for each block to minimize Cj xj. The optimal value will be an extreme point, say Vjh, or some point along some extreme ray, so we can generate the following column. Notice that there is a 1 at the bottom or the middle section there, and that's going to be the lambda that enters. I believe it would be lambda jh, and this means that there can only be one column entering from each block. So we will need m0 artificial variables to begin the simplex method. Suppose we have our basis now, and now we want to see if our solution is optimal. Our solution is simply the combination of all the corresponding extreme points with the lambdas and mu's in our basis. We will denote the corresponding dual solution as y bar, which is composed of y bar 0 and z bar. Y bar 0 is the part multiplying the constraints in the master problem, while z bar are the constraints that, z bar is the part that multiplies the constraints that ensure lambdas sum to 1. If we iterate through the simplex method, we see that we need to find y transpose ak minus ck greater than 0 at some point. This translates to the next line as we sub in the values from our problem. Notice going through the columns is like going through the vertices, so we want to check this for all the vertices. We can do this easily by splitting up into blocks again and looking for the max value of the first two parts of the equation. If we can't find a vertex that satisfies this, we have an optimal solution. If we can find a vertex that satisfies this, we simply generate the column and continue the simplex method. The following steps are actually done without any adjustments of the simplex method. This means unboundedness is calculated in the same way, and determining the leaving column is the same as well. In fact, there can only be unbounded answers if rays are in the final solution. The steps are here for good measure, and this completes the Dantzig-Wolfe decomposition. We note that in every iteration of the simplex method, we need to run the simplex method on each block. This turns out to be computationally more efficient than running the simplex method on the large problem, as inverting the large matrix would take more steps than inverting many small matrices. Now we will investigate the Bender's decomposition. Let's look at the typical setup, where the LP is written in two parts, complicating variables. And here they are, the complicating variables on the left and linking variables on the right. And this is similar to the Dantzig-Wolfe decomposition setup, but slightly rotated. Here we have the problem written out with the y being a vector of complicating variables and z a vector of linking variables. Suppose we fix a y equaling y bar. The problem then changes to the following, as c, y bar is now a constant, and we can move a 1 y bar around. We can then change it to its dual form, and the last two equations we'll call P1 and P2, and the dual we'll call PD. The maximum value of this modified problem will be found at some extreme point u in the feasible region defined by ua less than or equal to c. Now, this is starting to look familiar, as in the Dantzig-Wolfe decomposition, we also dealt with extreme points. We now introduce a master problem, just as in the Dantzig-Wolfe decomposition. We formulate this so that it's actually equivalent to the original problem, as this is created in a way such that the z values are dependent on the y values. We in fact subbed in the value u times b minus a1y in for c1z, as we know that the value of c1z is bounded by the dual solution PD. This is because u times b minus a1y is the objective value of the dual of P1, where P1 is solving for C1z. This actually allows us to keep finding cuts and adding constraints that bring us closer to the solution by choosing different y's. We see that this is somewhat similar to what we did in the Dantzig-Wolfe decomposition. However, we're now adding rows, while in the Dantzig-Wolfe decomposition we were adding columns. We can clearly have many cuts and add many more constraints, but how do we determine if a constraint should be in the master problem? We simply look at the subproblem dual and see if there is a solution there such that the value is greater than the current optimal value of z, which would be denoted by b, in the master problem. As soon as we cannot find any more, we know that we have arrived at the optimal value of the master problem and the optimal value of the original problem. The Dantzig-Wolfe decomposition is in fact the same idea, but working in the dual of the Bender's decomposition. Both decompositions rely on creating a master problem that is equivalent to the original and iterating through extreme points of subproblems to get to the solution. So in Bender's, we set our subproblems up based on the blocks of complicating variables, while in Dantzig-Wolfe, blocks will come in the form of complete constraints. The adding of the constraints in Bender's is equivalent to the column generation in the Dantzig-Wolfe decomposition. Both of the algorithms improve computational efficiency, because in each iteration we deal with many small matrices instead of the initial large matrix. And that concludes my presentation.